Okay. Um, so it shows being recorded, right, Katia?
Yeah.
Yeah, very good. Just because my screen shows a little differently. Anyway, so first of all, thank you very much for the invitation and the introduction. Um, and I will give a slightly funny talk in that I will spend a reasonable amount of time just discussing by now not very new results, but I do want to give a little bit of a twist on some of these. So I get to that. Well, I will say something early on, but I'll get to that more specifically later, really. This is the talk is based on mostly work with Plyman, Stefano, and Gunther Ruhlmann, actually mostly with Gunther, but I also mentioned some other the work of other people who contributed to this. Not I don't just mean to the subject, but to the actual results I present. Haoming Zhu, Martin de Hoop, and two of my current students, Joy Zhu and Evangelos Zakos. To get started, so I I will analyze variants of X-ray transforms. So just to recall, so what X-ray transforms are, you have a family of curves, for example, geodesics. So therefore, almost everything I say, the geodesics are irrelevant. So you have these on a domain or manifolded boundary or something like that, and you know the integrals of a function, or maybe it's a tensor, and you plug in the tangent vector of the curve into the tensor. Anyway, so if you know the integrals of a function along elements of this family, so you know what the integral of f of gamma of s ds is. The question is, can you find from this the function f? And so, of course, this can be interpreted in various ways. So you can, like the weakest statement you can ask is the transform f to if, an injective map. Another question you can ask, can you estimate f in terms of if? So a stability question. And you can also ask if there's some sort of a reconstruction algorithm. So I'm very far from being a numerical analyst. So in principle, reconstruction is about as good for me as anything can get. And you can also tweak this in various ways, for example, via spatial localization. You can ask if you have an open set O in this domain or manifolded boundary, wherever X. You can try to ask similar things for F restricted to O, using only the curves that stay within this region O. We'll have examples pretty soon. And so to be more concrete, so I said just curves. I mean, this could be like way too many curves. I want to consider families of curves that are parametrized, or maybe more precisely over-parametrized by the sphere bundle, Sx. So I don't really want to think of it as a unit sphere bundle. So I don't really want to think of metrics. If you want it, just the tangent bundle minus the zero section divided by dilation. So the length is not normalized; it's just the direction that you have. Of course, for geodesics, you can just normalize. I want to think that for each point x and each direction v, I have a curve gamma xv. And then my transform is, if at x comma v is just the integral of f along the curve gamma of x comma v. And so the overparameterization refers to the fact that, of course, if you take a fixed curve, fixed geodesic, then it's going to be of the form gamma x comma v for numerous xv, namely the various point tangent vector pairs along it. And so if you do now dimension counting, so the space of geodesics has a dimension 2n minus 2, right? So assuming the underlying space x has dimension n, right? Because the sphere is n minus 1 dimensional, so altogether it's 2n minus 1, so the base space plus the sphere in V. It's 2n minus 1, but because of this overparameterization, so you have a curve, so one-dimensional subset of these refers to exactly the same curve. It's really your data is 2n minus 2 dimensional. And so very formally, meaning this means nothing except if you really have some like Fourier integral operators, etc. So very formally, this map I is determined if n is equal to 2, because you are trying to recover a function of two variables that's n equals 2 from a function of 2n minus 2 variables, which is also 2 when n is 2. And is formally overdetermined if n is at least 3, because 2n minus 2 then is strictly bigger than n. And so what you expect is, again, this is purely a formal thing, but this is highly relevant if you actually have things like Fourier integral operators. So what you expect is some flexibility if the dimension is at least 3 of the underlying space, and little flexibility if n is equal to 2. So the two-dimensional problems are usually quite different flavor from the 3 and higher dimensional problems. So, so I mentioned that we are going to think about localized problems, as in all local curves or always some region. And so this is actually proved crucial even to obtain some global results. The way this will go is that I will have a function which for now denote by x tilde. And I will think about the super level set, so where x tilde is bigger than a constant minus c. So if you stare at the picture on the left, so x tilde is increasing as we're going up. So I made the, I didn't write it, and actually now I can write this. So on this slide, so x tilde equals 0 is the level set that's going right at the top of this So the picture you should have is that this is just Rn with the straight flat metric, so straight geodesics or straight curves. But I can't really draw a higher dimensional thing. This is Rn with n at least 3, but I can't really draw that. So I have these. So they have these level sets, and I'm going to be localizing to a region where this x tilde is bigger than some level like minus c. And then similarly on the right hand side, so on the left it's a nice non-singular function. So the level sets are all non-degenerate. On the right, I have a degenerate version. So it's it's like a ball foliated by the spheres. So that's also perfectly fine, but you always have to say something about this. So it's a bit slightly annoying, but it doesn't really make too much difference at the end of the day in this world. Okay, so analytically, what this localization will do. Did I say the words artificial boundary here? So we're going to think of, so say this is my x tilde equals minus c, and so I'm working in this shaded region. And so the really interesting thing is going to be this x tilde equals minus c. So that's what I'm going to refer to as the artificial boundary, and it's going to play a much more important role than the original boundary of the region. And what will happen in the approach I discussed is that it becomes a spatial infinity in what Marrow's called scattering pseudo differential algebra. So it's already showed up in works of other people, and they will mention this later on. But the thing I really hope to get to is some modifications of this framework, which in certain situations gives global results without the need for this localization. So I will explain why later on, why this is a good thing to do. I mean, plausible thing to do maybe. And even if you do localization, which you can do simultaneously, what will happen is that the size of the localization required becomes purely geometric, given by conjugate points. So what happened in this the first result I will explain. So with this localization, this work with Gunther, we had to localize to very small regions because a small parameter played a role, and this is eliminated, making everything purely geometric. And so the statement will be that suppose you have a function x tilde with strictly convex level sets, non-degenerate differential, and so the geodesics are again irrelevant. They could be curves, other families of curves. They do not have points conjugate to their points of tangential to the level set. So then the suitably defined normal operator, modified normal operator that I will describe later on, of the X-ray transform is a left invertible elliptic pseudo-differential operator and distribution supported in X. So you can actually get an invertibility statement, or this left invertibility. So that's the recovery of the input from the output of the X-ray transform. So that's what I hope to explain later on. But before doing that, I do want to say a little bit about at least quickly about some nonlinear applications. So maybe the most interesting thing is this boundary rigidity problem. so it connects to the X-ray transform via linearization, or even better, what really goes on is a pseudo-linearization. So this is a formula that first appeared in the work of Stefanov and Ullmann. And so the question here is that suppose you have a domain in a Riemannian manifold, and you have the distance function. The question is, does the restriction of the distance function to the boundary across the boundary determine the metric? And of course, it cannot really determine if there's an obvious obstacle, namely diffeomorphisms, preserving the boundary. But the question is if this is all. I mean, if you pull back the metric by diffeomorphism, that fixes the boundary pointwise. Of course, the distance function is not going to change. The geodesic just pull back. So there's also another version, which is the conformal problem, a fixed conformal class. So suppose you a priori know that G is is a multiple of a background metric G0, maybe the Euclidean metric, and you're looking for a sound speed or something like that. That would be the analog. And then there are no diffeomorphism obstacles. And the previous one, so the general question is a question in tensor tomography. This fixed conformal class problem is a question in the scalar version, or related to the scalar version. You certainly expect some geometric obstacles. So I mean, the distance function comes from locally length minimizing geodesics, and I mean, and so actually geodesics are locally length minimizing. Distance functions comes from the actual length minimizing. And so what you can do is you can change the metric in some region away from the boundary, and that will appear, the region where you change this can appear large, and then the distance minimizing geodesics will avoid it. So you do expect to put on some, have to put on some geometric assumptions. And Misha's conjecture from the early 80s is that for simple manifolds, so manifolds with strictly convex boundary on which the Riemannian exponential map is a diffeomorphism around each point, the manifold is determined by the boundary distance function up to the diffeomorphism invariance, so up to isometries, fixing the boundary. And so before our work with Plyman and Gunther, very little was known except in cases which have very different flavor. So the real analytic case, where the behavior of the boundary, of course, already tells you what's inside by sort of analytic continuation ideas. And two dimensions, which has a very different flavor for a number of reasons. I mean, both the geometry has a different flavor. Two-dimensional geometry feels very different from higher dimensional ones. Those are the tools you can use are quite different. So on simple manifolds, so remember this is that the geodesic exponential map around each point is a diffeomorphism in the domain. So in particular, you don't have conjugate points. So on simple manifolds, the boundary distance function, so the distance between points on the boundary going through the interior, remember the boundary is strictly convex. This determines the length relation, which in addition to the unique geodesic length between boundary points also gives you the direction in which these geodesics leave the boundary. So just knowing the travel times, you actually know the directions as well. So then you might as well just assume in the first place that you know the directions, and then the natural generalization is of the travel time problem. So it's travel time because one interpretation is that you look at if you look at the wave equation, solutions of the wave equation, singularities will propagate along geodesics. And the distance function between points on the boundary tell you how long it will take a wave to start at one point to reach the other point on the boundary. So a natural generalization of this to non-simple manifolds is the question if the length relation, so you throw in this extra information about directions, determines the metric up to diffeomorphism. And then here the prototypical result is due to Herglitz and Wihart and Zöpritz. So Wihart and Zöpritz are in geological applications, and so here what they showed is that for the ball, so you think of R3 in the fixed conformal class problem. So you have a background metric, in this case the Euclidean metric, and you are looking at a multiple of this, and you're going to look at spherically symmetric sound speeds. So the sound speed, so it's the multiple of the metric, depends on the radial function R only. the sound speed is determined from the boundary distance data, provided that R over CR prime is positive. And so here you can use one-dimensional techniques, the Abel transform. And so if you just do a little bit of computation, you will see that what this condition, this R over CR prime positive means, it's exactly that the spheres of radius R are strictly convex for the metric given by the sound speed. So, so in fact, this R, the radial function in this case, is the analog of this function x tilde I discussed earlier, whose level sets are supposed to be strictly convex. So in some sense, the strictly convex assumption that I mentioned earlier goes back to Herglotz, Swihart, and Zöpritz. So Misha made a different conjecture that's still open, but you know, maybe arguably one should have gone the Herglotz, Swihart, Zöpritz direction in hypothesis. So in any way, there's still plenty to do. And the theorem with Plyman and Gunther from 3 years ago at this point is that in 3 dimensions, if you have 2 Riemannian metrics, G and G tilde, and the boundary of this manifold with boundary is strictly convex with respect to both of them, and you have a function x tilde whose level sets are non-degenerate and strictly concave from the super level sets. So like the picture I had, and I think I will have again on the next slide or maybe 2 slides. So under all these assumptions, if the length relation of G and G tilde are the same, then there's a diffeomorphism fixing the boundary such that one is a pullback of the other. And so more geometrically, so when does such a function with this level, strictly convex or concave, we are looking at it, level set exists? Well, it exists, for instance, if you have a simply connected domain with non-positive sectional curvature, or more generally, if you have no focal point. So this is, then you can use, for x tilde, you can just use a distance from a boundary, from a point just outside the boundary. So you have this domain x, go a little bit outside, take a point, and take the distance spheres. Well, renormalize if you want it, normalize the way I had it before. Yeah, so here's the picture. So the left-hand side is the example as the theorem as I stated it. And so you have this function x tilde with level sets that are strictly concave from the super level sets, so from above. And so the theorem would apply to this. The right-hand side has a degenerate level set at the origin, but in fact, there's a simple modification of the theorem that would cover this, and which I don't want to state formally because I want to get to other things. And then, so with the simple modification, the assumption holds also if this metric has, so the metric for which you needed this convexity conditions as one of the metrics, has non-negative curvature due to the work of Paternine, Salo, Ullman, and Zhu. So it's sort of funny that both negative curvature or non-positive curvature and positive curvature are very good, but of course, you know, you could vary from place to place, and then things are less good. So the result is proved. But again, this curvature condition is just a way of guaranteeing the existence of such a convex function. It might exist for other reasons. Also, you really, I'm phrasing this in the simplest possible way. You don't really need a single function with this property. You could use a number of different functions sort of in parallel. And the reason is that you really prove this theorem by localization. The sort of thing that you will do is you go little by little. That first you're going to recover the metric, say near the stop region, and then you go a little bit beyond, etc. And you could also come from like different sides and sort of try to chop down parts of the domain, etc. So you actually have quite a bit of flexibility, and it's not completely clear, certainly to me, and I think to us at this point, what the optimal geometric assumption is for this result to work. So I also want to say just a little bit about other nonlinear results. So Riemannian geometry is not the only thing in the world. That are sort of very related. So one of them is the recovery of elastic parameters in anisotropic elasticity. So isotropic elasticity is very much like the Riemannian metric problem introduces to a special Riemannian problem. But anisotropic elasticity is really much richer than Riemannian geometry. And in this case, this linearization or pseudo-linearization gives you a related kind of X-ray transform along integral curves of the Hamilton vector field corresponding to the different wave speeds. So for these elastic problems, there are different ways. There are, whoops, this QV should be a QP. There's a P waves and S waves, so quasi-P and quasi-S, because of this breaking of the isotropy. So this SH and the QS are sort of S waves, and the QPs are, just correct it right now, QP. So this QPs are the P waves of isotropic elasticity. And so one reason why this is interesting is because in this case, these curves along which you're doing this modified X-ray transform for the pseudo-linearization are naturally parameterized by the phase space. So of course you could say the same thing for the geodesics, but for the geodesics, it's neither here nor there. You can do either one. But for this, you don't really have an option in general. You really are parameterized by the phase space, the cosphere bundle. And the map from the cosphere bundle to the sphere bundle is often not injective. So there are multiple cotangent vectors that will give you the same tangent vector. So this is called something like wave triplication in some cases. And with Martin de Hoop and Gunther Ullmann, we obtained results on the recovery of certain elastic parameters in this transversely anisotropic setting, which I didn't go into, but so just an indication of other things one can do. But these are basic analogs of the results that I will discuss. Well, the metric result above, and then various other things I do below. So nice, where sort of nice theory works, and their new results by Joy Zhu, is my PhD student, will be finishing next year. Which goes significantly beyond this framework by developing a new sort of parabolic scaling, so rather than elliptic version of this technique, in analogy with the work of Boutier de Monvel in circa 70 in the sort of standard PDE world. So there are many further directions. And let me just say one more thing about the linear problem that I won't really get into. So, so you can also consider, of course, the X-ray transform in other situations, such as the large ends of cones. So you can also talk about, by the way, let's say hyperbolic space, in which Guillermo, Ullmann, and others worked recently. Stepanov and Graham and others worked recently. In this conic setting. So you can think about the geodesic X-ray transform manifold that's asymptotic to a cone. And so asymptotic to a cone meaning the large end of a cone. So of course an example is the Euclidean metric. Here the cone is just a cone over a sphere. And this geometry, such a metric, is actually the thing that induces Marrow's scattering algebra, which I already mentioned in terms of this artificial boundary localization. And so very interestingly, last year, Guillermo and Su showed that if there are no conjugate points or the curvature is negative, then the X-ray transform on such spaces is injective, acting on appropriate polynomially weighted function spaces. And then there was also a remarkable companion paper of Guillermo, Mazzucchelli, and Su, which showed that actually asymptotically Euclidean metric, so when you're asymptotic to the actual Euclidean metric, so your sphere at infinity is really the standard sphere, so asymptotic Euclidean metric without conjugate points. So this is a purely geometry statement now. Asymptotic Euclidean metrics, so the conjugate points are flat. So they are the Euclidean metric. So the absence of conjugate points in the X-ray transform statement, the previous paragraph, is sort of a strong hypothesis in this sense. So if you perturb the Euclidean metric, then actually you can't expect to get away without conjugate points. So the last sort of statement I wanted to make, that's not directly the main subject of my talk, but it's closely related to in terms of technology. So this is a work in progress that hopefully should be finished very soon. I mean, on the scale of month or so. So this is the PhD thesis of my finishing student Evangelos Zakos, and this uses yet another different differential algebra, which at least temporarily is called the one-cusp algebra, or its semi-classical version in the approach I will discuss later in the talk. And what this will tell you is that if you have a manifold of dimension at least 3 with a metric asymptotic to a cone, and the cone's link cross section is close to a standard unit sphere, then in a colored neighborhood of infinity, the geodesic X-ray transform is actually injective on appropriate weighted spaces. And at this point, the weights are sort of ridiculously bad. So you need like Gaussian decay, but that's what somehow works out nicely with the analytic setup in this case. So the main point was I was trying to give some sort of general discussion of like where one can go, what sort of problems one can look at using the X-ray transform techniques. And then the remainder of this talk, I will sort of get back to scratch and so start from scratch and discuss the X-ray transform and what convexity and what convexity buys and what sort of analytic techniques enter. So so actually for now, let's be really down to earth and just think about Rn. And of course, then the Euclidean X-ray transform is super well understood, right? So if you know the integral along lines, then you know the integral of planes, hyperplanes. That's a radon transform, and then you can use that to build up the Fourier transform, and that you know how to invert. And an interesting thing though is if you dimension at least 3, then you don't have to go this way, full way that I just discussed. Instead, you can just slice Rn by 2 planes and inverse the transform just using geodesics in the 2 planes. So I think the next slide has a picture. So X is my domain, so it's like say a ball, bit of a ball, and that's shown. And X tilde is your Rn. And in order to find a function from its integrals on geodesics, I can just take these 2 planes. So we're in 3 dimensions for this picture. I think this is my most sophisticated picture probably, which is not a good sign, but anyway. So you slice it with this 2 planes and just use the invertibility of the X-ray transform in these 2 planes to recover a function from its integrals along the straight lines. And the neat thing is that if X is a strictly convex domain, so the boundary is strictly convex, you are in these 3 dimensions, then this means that you can just use planes that are parallel, and you take a point P on the boundary, like in the picture, you can just use planes that are parallel to the tangent plane at P. And this means, because of strict convexity of the domain, that you're only using local geodesics, so that are in a neighborhood, restricted to a neighborhood of P, in order to reconstruct F near P. So that gives you a hint that there's a local problem that you can do. And then the question is, of course, can you do some weaker version? I mean, the chances that you can just use things in a plane is just about 0, because geodesics will not be contained in a plane. But like geodesics through a point starting a plane will not be in that plane. But maybe some weaker version where you give yourself a bit more information. And the other thing is that, so it's first of all interesting that you can localize, but also the other part is that answering this question for certain small sets O, like this local invertibility, actually also answers the global question. So does the X-ray transform give you the function globally? by a layer stripping argument that I will discuss a bit later. So it's not just for the sake of the local problem that's interesting enough, I think, and that's why actually Gunther and I started thinking about this, I think, in the first place. So the local problem is interesting, but there's this global implication. So, okay, now what we'd like is that if you have a small set O, so maybe a small neighborhood of a point in the boundary, and you would like to recover a function in this set O by integrals of from integrals of the function along geodesics, which on this picture are straight lines that are confined to the domain, meaning that, of course, they will, here in the picture, you have an Rn, you have a domain. Of course, the straight lines will exit, but the point is they exit through the actual boundary of the domain. So they don't cross this sort of artificial boundary that's the bottom of O. So they're sort of short segments. So of course, in general, if you don't have convexity of the boundary, you can't expect too much. But if the boundary is strictly convex, then there are plenty which are almost tangent to the boundary, like on the picture. And so all those geodesics are very good because, you know, using only local information, like the integral along these geodesics, so straight lines in the picture, only depends on f restricted to this domain. So it's reasonable to expect to have some sort of potentially at least some sort of invertibility theory. Now, of course, it's not enough to have some geodesics. You need lots of such geodesics through every point, and this is achieved in the framework I described. So if you have a function which I'm calling x tilde here, whose level sets are strictly concave from the super level sets, and so normalized as I mentioned before. And again, you look at the super level sets, which again is an artificial boundary. So I think I have the same picture again I had before. It's a different, some combined version of the picture. So again, x tilde is, so at P here, x tilde is equal to 0. So the level set would be something like this. This is the x tilde equals 0 level set. And then the x tilde equals minus c on the bottom. I really work in this crescent-shaped region, so these regions will give me enough geodesics, basically by, so here's a point at z on this picture. So again, I take the level set. This is x tilde equals some new constant through z, and I will take geodesics that are almost tangent to this level set. And you can easily, whenever you have a point at which the boundary is strictly convex, it's a purely local thing, you can easily construct such a function locally, and so everything will be fine. Okay, so the local result, so on some of these slides I edited this morning, so I hope I didn't introduce any new typos. So the local results with Gunther from 2012 is that, again, the dimension is at least 3, and I take these regions O of C. So O of C is just the region where this x tilde is, so this is my region O of C, where x tilde is bigger than minus C. So on such regions for sufficiently small c, so that's important, sufficiently small small c that enters crucially in the actual proof. So anyway, so for sufficiently small c, this this X-ray transform is injective. So here I'm considering the X-ray transform just restricted to the O local geodesics. So it's injective on HS functions, and moreover, you get an estimate, a weighted estimate of the way I wrote this down to an exponentially weighted, where the weight is super weak. It's exponentially weak at the artificial boundary. That's, so this is this is equal to 0 at the artificial boundary. So I'm allowing exponential growth at the artificial boundary. So I got an estimate in these weighted Sobolev spaces. And so we proved this for geodesics, and Hamming-Zhu noticed that in fact you can do a small change and everything works for general families of curves. Small change in argument, everything works in the general family of curves, which is very neat. Okay, so I think I already commented on that. And in order to, so this is a local statement. In order to go further, you want to say that various things are uniform. Like I had, so I think it was 2 slides before. My boundary was rho equals 0. I could go to another level set of rho. So rho equals 0 is the actual boundary. I go to rho equals something tiny, positive or negative, doesn't really matter. The point is that the statement that we had is uniform in various things. Like maybe I want to change the boundary a bit. Maybe I want to change the artificial boundary a bit, etc. And this uniformity is what allows for the layer stripping algorithm. And the method is constructive to the extent that I mean, you're doing a construction in absolute differential operator algebra, and so that's constructive. And at the end of the day, you have to sum a convergent Neumann series because you get going to actually a small error. And then maybe I'm going to now skip this layer stripping part. I mean, except that maybe say that you just, as I discussed, you go sort of little by little. You know, first recover the function in the stop region, which is supposed to be tiny. The tiny comes from this parameter C, how far you went, having to be small in order for the analytic methods to apply. And then you go a bit further, and then you go a bit further, etc. And the uniformity I mentioned, the parameters assures that you actually can do this and get done in sort of finitely many steps if in a part of the domain that you can where you really have this non-degeneracy hypothesis. Of course, here in the right-hand side on the on this ball, what you get is that in the complement of any positive radius ball, so in a region like any annulus like this, you get this determination in finite number of steps, and that's enough for an injectivity statement. Okay, okay, so I should say that there have been a number of global uniqueness and stability results. So Muhammadov, Romanov, Friedrich, Stefanov, and Ullmann. But you know, there were no local results prior to this, even for metrics conformal to the Euclidean case. Of course, the Euclidean case is obvious, as I discussed at the beginning. And I already mentioned that this convexity condition is the Hergot-Zwieher-Zupritz condition. And I should also say that more recently, Guillermo and part of its collaborators also proved X-ray injectivity and related results in negative curvature, which it's sort of going in a, well, both technology-wise, but also assumption-wise, going in a somewhat different direction. So like negative curvature and related things, like also flows. And okay, so I want to spend the end of the talk on the analysis. So the proof of this local theorem, as well as maybe globalizing it in some way. I mean, not the layer stripping, but some direct global version. And so the idea is that, and this goes back to the work of Stefanov and Ullmann earlier on, is to consider a localizer, so some multiplication operator Q, on my parameter space for the geodesics. So this would be the sphere bundle of, okay, maybe instead of thinking about my actual domain X, I want to think about the slightly extended version, that's the tilde. I think I haven't been very careful about what's X and what's X tilde in the next slides. So what I want to do is I want to use basically a normal operator like I star I, but I want to sort of cut down the information, and that's what this Q does, that I only take certain geodesics or curves into account. And right, generally the point of this I star I or this I star QI is that under geometric assumptions like no conjugate points, it will produce your pseudo differential operator from the initial Fourier integral operator, and then you can use the pseudo differential operator machinery. And so, of course, if you put in a cutoff, then it's only non-conjugacy along the geodesics corresponding to this supportive Q that enters. And locally, it's always satisfied. So for local theory, there's no like what in this work with Gunther, there's no issues. Just recall that the principal symbol in the pseudo-differential operator algebras captures the leading order behavior as the momentum variable or frequency variable goes to infinity. And in compact settings, that's enough to capture the operator modulo relatively compact operators on manifolded boundaries. Now, when you have a classical operator, so ellipticity is a lower bound. When you have a classical operator, so it has a homogeneous principal symbol, so this is a scalar setting, the ellipticity is just a non-vanishing condition for the principal symbol. And then once you have that, then you get a Fredholm statement between appropriate function spaces and approximate inverses and things like that. So concretely for this X-ray transform, the principal symbol of this modified version, I star Qi, is a multiple of basically an integral of the function little q by which big Q is multiplying, evaluated on the kernel of the covector zeta at which I'm trying to evaluate the principal symbol. So zeta is a covector, so its kernel is a subspace of the tangent space. And of course, I'm now restricting to just the curves I'm considering, so sitting in the sphere bundle. And I just have to integrate with respect to some positive density, depending on exactly how you define things. And the upshot is that this operator is going to be elliptic, provided that my multiplier is non-negative. And in addition, for any covector zeta, there's a vector v annihilated by it. So that's going to be one of these v perps, such that q applied to evaluate that z comma v is non-zero. So you're putting actually a positive weight on something. And so this suffices, having ellipticity suffices for a semi-Fredholm theory. So you see that the null space in supported distributions is finite dimensional. One has a stability estimate on the complementary subspace of this finite dimensional space, etc. So things are relatively good. But the problem is that you still have this finite and possibly huge dimensional null space. And in order to remove this, it's very useful to have a small parameter. There are at least two options. And both of the ones I'm going to mention use this convex foliation. And what I'm going to do is I'm going to write tangent vectors as, so I'm using a little bit more than the foliation in this writing, like I say, using a product decomposition locally. So I'm writing tangent vectors as lambda times the derivative in x plus omega times the derivative in y, where the y is coordinates from the level sets of x. So this x is what I called x tilde before. And I'm going to make this lambda sufficiently small. So I'm going to work with almost tangent to the level set geodesics or curves in general. And the key point is that if the dimension is at least 3, then given any direction zeta in the Cauchy bundle, or cotangent vector, maybe I should have said even, there's a tangent vector annihilated by it that's tangent to the level set of x. So, right, so the annihilated by zeta is a codimension 1 condition, and the tangent space is also one-dimensional, I mean codimension 1, and so the intersection will have will be non-trivial. So so this is really where the at least 3-dimensionality enters. Okay, so now these two approaches are the following. So one, and this is what Gunther and I did earlier, we work in a small, so this really meaning thin region, via adding an artificial boundary as discussed. And in this case, the thinness, so that was this parameter c that we work in x tilde bigger than minus c. So that thinness is really the small parameter that will appear analytically. And this will come from rapid vanishing of errors of the parametrics construction at the artificial boundary. So if I call the artificial boundary x equals 0, so x will be something like x tilde plus c. So that's what entered in the weight, exponential weight I described before. Then I will basically take my q to be a function of lambda. So remember that was the lambda is the normal component, so normal to the level set. So normal component of the momentum. So that says as x goes to towards 0, so we're getting close to the artificial boundary, then we are more and more localized to tangent geodesics. And this conservatively, meaning that even square root x would be fine, assures that the geodesics do not cross the artificial boundary. The other version is you can work globally, but in this case you make your q depend on a semi-classical parameter h. So in this case, you do not need, but you can use an artificial boundary. And if you don't use an artificial boundary, then your cutoff can be a function of lambda over square root h. And so this is the new approach that I will briefly outline the remaining few minutes. Of course, as I said, you can combine. So we have both the artificial boundary and the semi-classical parameter, and then you have this combined cutoff. And in both cases, use exponential weights. So you really have extra exponential conjugation. And in both cases, what happens is that, so in the first case, this is just as I stated in the theorem with Gunther, you have a weight that's like an exponential of a constant over x. So this is a positive constant. And this allows for exponential growth at this artificial boundary, and the estimates get weaker as you get towards the artificial boundary. And in the other setting, you look at something like e to the minus x over h. So now x is could be whatever sign, right? I mean, we don't have a boundary. So maybe this is this function x tilde that I had before. And again, the estimate gets weaker as x decreases. So that's in both cases, this weight is in the relevant region. So in the first case, x positive. In the second case, just anything is a decreasing function of x. And with the strict convexity of this level sets of x, this means that this conjugated operator puts little weight, meaning a vanishing portion as the parameters tend to 0, to the non-completely local portion of the Schwartz kernel. So the Schwartz kernel of this operator, I star I, modified I star I, of course, is a global object, but the part away from the diagonal will get little weight. In fact, the vanishing portion as the parameters go to 0. And so we have very little weight in this limit, which is what really helps. Okay, and so in the semi-classical setting, what you get is not quite a standard semi-classical operator. You can sort of think about it like that as a not quite optimal version of a semi-classical operator. It's a sort of foliation operator where which is built out of vector fields that are, you basically take h times all vector fields and square root of h times the vector fields tangent to the level sets of this function x. So it's you basically build out of h dx and square root of h times dy. And you do a corresponding quantization. So the dual to x variable c is quantized with an over h, and the dual to y variable eta is quantized by a square root of h. And where the actual symbols are just the usual kind of symbols. And this still allows for the usual symbol calculus, which gains square root h in each step of the asymptotic expansions. Now the principal symbol of this operator is considered both in the sense as the momentum. So here now as a semi-classical momentum variable goes to infinity, and as a semi-classical parameter goes to 0. So the quotient that you are taking is really square root of h times order n minus 1 symbols. And you have the usual thing that the principal symbol is elliptic, and there's a parametrics whose error is order h to the infinity. And so that actually means also small, not just compact, but small. And so you get the identity plus that is invertible on appropriate function spaces. And so the statement is that the proposition in the end is that for appropriate chi, so you have to do something about, specify it a little bit more, that I didn't want to do this. This conjugated operator, in fact, is elliptic in this full sense. And so as I mentioned before, this is enough to give things like left inverses by the usual kind of arguments. Okay, so let me just make the analogy with and finish with that with the earlier work with Gunther, where you had this artificial boundary which is made x equals 0. So say here that x equals 0 is the artificial boundary. So there the analogous statement was that this conjugated modified normal operator is an elliptic scattering pseudo-differential operator, and so elliptic in this full sense. And so it's completely analogous to what I stated in the semi-classical setting. And this algebra, the scattering pseudo-differential operator algebra, is something that's familiar really to a lot of people, because it's just one of the standard Hermander algebras, which in this case goes back to Parenti and Shubin. So Mara was put into a more geometric version. But let me write it out in the compactified version. So here it is. Here's what the algebra quantization looks like in the compactified version. So what happened is that I have this, in this quantization map, I have this division by x squared, respectively x, for the x and y dual variables. And that's what converts to the derivatives that you normally have in a quantization to x squared dx, respectively x dy. And the actual amplitude a is just a standard symbol. And the point is that this gives you a symbol calculus as well as x goes to 0, gaining an x in each step of the asymptotic expansion. So this is completely analogous to the semi-classical setting I stated, with the comparison being, so I wrote down again the quantization map. The comparison is that x is behaving like square root of h. Just to connect back to the more familiar version of the classical, for sort of classical analysts, where if you want to think about having an infinity out there, this is just a Hermander algebra on Rn, so locally anyway, it's a Hermander algebra on Rn, where you have a symbol class where you, so z is the position, zeta is the momentum. If you differentiate the momentum, you get decay in the momentum. If you differentiate in the position, you get decay in the position. So again, it's one of the, it goes back to Shubin and Parenti, and it's one of the standard Hermander algebras. And you can just localize in general on manifolded boundary to like conic regions in Rn. That's what the conversion is. And then if you think about it this way, if you're looking at the cone where say Zn is relatively large, the nth coordinate is relatively large, then the identification to the local version is x. That was my boundary defining function, is Zn inverse, and yj's are zj over zn. And the so the standard principal symbol in this pseudo-differential operator algebra, again, is usually is gaining in terms of the zeta behavior, which does not capture compactness. But we have ellipticity, the same reason in Stefanov and Ullmann. And then here's my last slide. To get the full ellipticity, you really want to keep track of this improvement also in the z variable, the position variable. So you're really quotienting out by decay, gaining decay there as well. And what happens is that in fact, with choosing an appropriate cutoff, which approximates a Gaussian, you can actually show that you have full ellipticity, which will give you Fredholm theory to start with. But if the region is thin enough, then that means that your errors, which gain powers of x, like x to the infinity, they're actually tiny. and that's actually gives the invertibility using this thinness of the region. So there are two versions now, the thinness of the region and the semi-classical parameter that can give you invertibility. And the nonlinear problems like the fixed conformal class problem is completely similar with the microlocally weighted transform, and the actual metric problems are, of course, tensor problems, and they're more complicated. Thank you very much for your attention.
Thank you very much, Andras. Thank you very much. Are there any questions or comments?
Let's see, this is Margaret Cheney. Can you hear me? I'm wondering about the applicability to sonar, where you have waves bouncing up and down in a waveguide. You know, the waves bounce off the bottom and part of it gets reflected, part of it also goes into the bottom. So I think that would correspond to a case where you had a discontinuity in your metric, and then you would be seeing multiple arrival times, multiple arrivals from multiple paths, you know, both the direct path and multi-bounce paths. And then those extra multi-bounce paths are almost effectively giving you sort of more sensors. I'm wondering if there's any theory about this and if anybody's thinking about that. Thanks.
So, okay, so what I can say is that there's so I don't know about the sonar in particular, but a somewhat similar setting with discontinuities is sort of seismic imaging, where you have your material parameters jump along some hypersurfaces. And so there's work of Martin de Hoop, Gunther Ullmann, Peter Kadai, and Vitali Katznelson, as well as Gunther Pleiman and myself on such settings. So, but there, so we still have the advantage. So a picture would be like this: that you have this big ball or something, and then you may have. So these are the these might be the discontinuities. So what you do is the approach that I described. So I think I should have made some things more curved because it's a bit hard to. So the approach I described, it proceeds by going in sort of thin regions like this, sort of little by little. And if you do this, then using geodesics or Weber curves that stay in this region. And so if you go like this, then of course initially you don't see the discontinuities, so you can go all the way to the actual discontinuity, the first discontinuity. And then, so you have to do a somewhat careful analysis, of course, of exactly what reflects and how it behaves. And so this was first, a version of this was first discussed in this work of Martin de Hoop and the collaborators I mentioned. And then also Pleiman, Gunther, and I did some work in this regard. So I think it has some similarity with the sonar, but I'm not quite sure whether you have this localization feature that you can go. I mean, at some point you recover things up to the first discontinuity, then effectively you think of making the first discontinuity as your boundary and proceed further. So the point is that there's still a lot of arrays that don't bounce, and you can use these. So if you really have everything is bouncing all the time, then I'm not sure.
I'm wondering if you can exploit those multiple bounces because they're effectively giving you more views of your region.
So that's possible, but I would have to think about the geometry. I mean, in the case of this seismic problem, you can definitely exploit that. It's very helpful, but it's also helping you that you can proceed partly like you somehow want to put them into hierarchy. So that's what I think Martin de Hoop and others called something like a scattering. I don't know. I mean, some of those scattering series, I forget exactly what they're called. So you want to put them in some sort of hierarchy because otherwise it's just sort of too much coming at you. So in this, so one way of organizing the hierarchy is what I described. So I don't know whether that applies in the sonar case, but certainly as soon as you can somehow organize your hierarchy, you have a chance. But you have to be somehow able to organize it.
Yeah, thanks.
Thank you very much. Are there any further questions or comments?
Yeah, I have a question.
Please, please.
Lauren, okay. So, Andras, so you said at the beginning, not the beginning, somewhere in the middle, that you don't need artificial boundary for this semi-classical trick. But then what is even X in that case?
So no, I mean, you do want a function with this strictly convex level set. So you still need the, so the strictly convex level sets are still important. So there's a strong hypothesis.
But it could be, for example, distance to some artificial boundary, which roughly speaking is even outside of the manifolds. So this is one more.
Sure. I mean, the way I would put this is that this doesn't really give you anything that we didn't know how to do in the first place. But it at least for the standard X-ray transform on domains with boundaries. But it somehow makes how big regions you take in the steps more geometric. So it's really the conjugate points that determine the behavior. And one of the things is that for the to get this the actual local, I mean, like in local meaning step by step injectivity, we have to take very very thin regions, and for this, and we have to do some sort of a sort of uniform analysis that as this the thinness goes to zero, things go on, and so this can be more complicated in other geometric settings. So the one of the reasons why I mentioned the cone, the large end of cones, is exactly because there I think it's a bit harder to do directly this sort of thinness version of the analysis.
Yeah, but if you want to prove a local result, it can still be a distance to artificial boundary, right? If you really insist.
That's right. That's right. Yeah. So if you want to, exactly. So if you are in the setting where you're doing the like what we were working on, the main thing is that you don't have to make the region so small. So basically, what you just need to exclude actually, at least for the X-ray transform, rather than the nonlinear problem, you just have to exclude conjugate points.
Yeah. Okay. Very interesting. Thank you.
Thank you. Are there any further questions or comments?
May I please ask a question?
Please.
Yes. I want to ask a question about ellipticity. But before, in order to make sure that I understood correctly, I want to ask something about the artificial boundary case. So I was thinking that irrespective of the ellipticity, scatterings to differential operators have principal symbol at the boundary too in general. And this needs to be invertible globally to imply Fredholm properties.
Yeah.
However, the differential operator is degenerate at the artificial boundary. So how do you overcome this problem?
Oh no, it's not degenerate. So this is the thing. It's not degenerate as the right kind of object. So degenerate always depends on the sort of the goggles or glasses or whatever one puts on, and if you think of them in terms of like standard differential operators like dx and dy, of course they look degenerate, but that just says that the standard way of looking at it is not the right way of looking at it. So I mean, I think this actually happens quite a lot in mathematics, that one says that something doesn't work, but really it doesn't work when one thinks of it in a certain framework, and you always have to go to the right framework to think about it. So ellipticity really means that you have an elliptic combination of things like x squared dx and x dy j. So something like so say in 2 dimensions, something like this: x squared dx squared plus x dy squared plus 1. This would be an elliptic operator. Okay, and the principal symbol, I think with the notation I had, would be the full principal symbol would be like c tilde squared plus eta tilde squared plus 1. This is the principal symbol. So you have to think of this x squared dx. This is a block, and x dy again is a block, like a block, and so that also that's converted to x tilde. The comparison is it's exactly like the semi-classical algebra, right? Where you would have something like h dx squared plus h dy squared. So let's do the standard semi-classical algebra plus 1. And here the conversion would be something like c squared plus eta squared plus 1. So that would be the semi-classical principal symbol. So even though there's an h here, this is, again, a block. So you shouldn't think of this as a degenerate operator. It's actually a completely non-degenerate operator. It's degenerate if one thinks of it in the wrong way.
Okay. Thank you very much. Can I ask another question about ellipticity? Because you mentioned the radial compactification of Rn, and when you mentioned it, what came to my mind was the following: that even thinking, let's say, the inversion of the Laplacian in case of functions or one forms, and you would still have issues at the zero section because your localization supports the zero. Yeah. So I was thinking that in such a case, if you were thinking, let's say, the solenoidal gates, it would be it would not be fully elliptic. And if you thought, for example, a different type, let's say the normal gates, then again, if you added potential fields, it would end up as an evolution equation. So how is ellipticity not lost?
Oh, so for these, so first of all, so here what I have in this was the Laplacian plus 1, right? That's what in this scattering example. Okay, so the Laplacian plus 1 is fine. Now, if you go to the so of course in these inverse problems, you don't actually get the Laplacian. You get some other operator, and so it's a separate question from there. But if you really want to think about the Laplacian, you do lose ellipticity. There's no question about that. And the scattering algebra is not quite the right algebra to think about the Laplacian directly. So it's a resolution of the scattering algebras, or a second microlocalization. That's the right way of doing it. The cheap way of doing it is Merrill's B algebra. The real way of doing it is second microlocalization. But in any case, if you don't want to do that, and so what enters into your actual inverse problem question is that you shouldn't use the standard solenoidal gauge, because that gives rise to Laplacian, which, as you say, is bad. What you should use instead is an exponentially conjugated version. So you know the gauge is a gauge. It's a completely artificial thing. It's not a real thing. So you want to choose it in a way that works well with your problem. And so what we did with Plamen and Gunther is to for the tensor results is to use a gauge where you conjugate your divergence operator by an exponential factor. So it's like a e to the constant over x, where x is your boundary defining function, and that is what changes the ellipticity character.
Okay, thank you very much. Are there any further questions or comments?
Okay, thank you.
Thank you. Okay, if not, thank you very much, Andras. Thank you very much. And thank you very much, everyone, for joining the seminar. Thank you very much. Thank you.
Thank you, Katya. So I'm going to stop the recording.